Okay, I guess we can start now. Others will join as we go. So this is the first live problem solving session for the course, the NPTEL course, Aqueous Corrosion and Control. I'm the only TA for this course, Manjeet. I'm a PhD student at IIT Delhi. If you have any doubts, you can always mail me or ask your doubt on the forum on the NPTEL course website. Just to put a face to the name, as my picture, I don't have that camera on this PC. Hopefully, you can see. So, what some details about the live problem solving session? So, this session will happen at every Tuesday from 6 to 8. There might be some rescheduling depending if I have to travel somewhere, but you guys will be informed through the portal again in the announcement section of on the NPTEL course if there is any changes. So these problem solving sessions will have 4 components. First, I'll briefly recap the topics covered in the video lecture for that week. I'll have some practice questions and I'll also discuss the previous week's assignment there. And at the end, if you guys have any doubts, you can ask me in the session itself or later. Just drop me an email. Okay. I'm yet to populate the sheet, but this is first week. We'll have 12 sessions, and the 13th session, uh, depending on like if you need a revision session at the end, covering the entire course before the exam. And yeah, so I think there's a deadline coming up for registration for the exam. That's all that I'm seeing. Yes, 24th Feb, 5 p.m. If you want to get a certificate for this course, you can register for the exam and pay, I think, 1,000 rupees of exam fee. You need to do this before 24th Feb. Pay the fees and register for the exam. Exam date will be in May, 4th May. So we'll have this doubt solving session maybe a week or two before the session and before the exam. Okay. These this is the Zoom link for the problem solving session. It will remain the same. Either you can bookmark it or every week you also send a mail regarding the meeting link. So it's okay. I'll record all these sessions and upload them on YouTube. This is the channel. If there's any changes to this, I'll update it in the next session. I'll also upload this PPT on a Google Drive. Again, I'll upload the link and paste the link here once let's upload this first slide. Okay, so just beginning with the brief. We had 3 lectures to cover in this week. So first was just a general introduction of the course. So why does corrosion happen? So all the metals we know are most of the metals except the noble metals like platinum, gold, iridium, rhodium, like those metals. Most of these metals or other metals are always present in some form of ore, sulfide or oxide. So we need to purify and like reduce the metal inside the ore to get the pure metal, then use that metal for whatever application we want. That reduction from ore requires some, we need to input energy into the system. So we break the bond between, so suppose if we have ferrite iron oxide, so we need to uh, separate the oxygen and the iron. So we need to supply some uh, energy to it. So this metal is at higher energy state than the ore. So what will happen eventually is it will have some tendency to reduce energy. Everything wants to be at the lowest energy possible in the world. That's what the metal will also try. Given the opportunity to react, it will react and form a lower energy state material. For iron again, iron will rust in presence of oxygen and some other uh, like um, electrolyte. So usually whenever there is some moisture, water absorbed on the surface, the oxygen will dissolve in it and react with the metal, giving you metal oxide or iron oxide. Like that, it will form, and yeah, that's why the corrosion happens. So as I mentioned, we need electrolyte for the oxidation to occur. If there is no electrolyte, if there is no oxidizing species inside the metal, the metal concentration in the solution and the metal will remain constant. So some some iron may lose electrons there. If we will lose some electrons due to electrons, but those electrons will be absorbed by some other Fe ions, so Fe ions, Fe plus two, and it will get absorbed. It will yeah, um, get back on the surface of the metal, the iron, the reduced iron. This is what equilibrium, and this reaction is going on in equilibrium. So Fe gives Fe plus two electrons. This is in equilibrium, so happening on both directions. So yeah, so this equilibrium concentration of this metal is maintained. There are no oxidizing species. However, if there is a oxidizing species present, so in this case there's H plus ion. So these free electrons given by this iron, so iron Fe gives Fe plus two electrons. So these two electrons are then taken up by the hydrogen plus ions, and you get H plus two electrons gives you H2, and this H2 will leave this is a gas, so I will get uh, dissolved in the solution, or it will leave as bubbles on the surface. Okay, so what will happen eventually is, so the hydrogen in the solution is getting depleted, so reaction is proceeding in this direction. The electrons here are getting consumed, so this reaction is also proceeding this way. So eventually, all the Fe will get converted into Fe plus 2, given that there is sufficient H plus ions in the solution. Okay, so this is just in case, just an example where just H plus is present. If we had O2, maybe the O2 would take up the electron and form maybe OH minus, something like that in the solution. So other reactions may proceed, but yeah, this is giving an example. So there are both oxidation and reduction reactions happening on the surface or near the surface. Oxidation is whenever something loses the electron. So metal is getting oxidized to metal plus 2 or metal plus, giving out 2 electrons. And these 2 electrons are accepted by the oxidant, electron acceptors, plus hydrogen plus or metal plus or O2. These are the oxidants which oxidize the metal. So the metal is getting oxidized, and these elements, they have the tendency to oxidize the metal. So they'll accept the metal electrons from the metal. So thus we are saying they're oxidizing the metal. The reduced species are there, like hydrogen, whatever finally is formed, like OH minus, or even you can have different metal, like here it's some metal M, it can be metal N. So M plus N, you can get M plus N. So this N plus has taken electron from this metal M. So like this can also happen. Like this is not hydrogen, this call it X maybe, just to avoid confusion. Okay. So there are different techniques to mitigate corrosion. So you can have sacrificial metal, which is if you have iron, you can have a layer of zinc on top, where the zinc will oxidize first, forming Zn plus 2, leaving the iron intact, thus protecting the iron. Or you can have passive film formation. Here you have this uh, iron metal oxide, metal O, metal oxide. So in case of aluminum, this can be Al2O3, aluminum oxide layer. This forms on the surface and it prevents further oxidant from reaching this metal surface. So in case H plus, it won't be able to penetrate this passive film of aluminum side, and the rest of the aluminum would not corrode. Only a thin layer on the surface would get corroded. Aluminum is one, titanium is another example, titanium oxide. Okay. And there are some examples. So type of corrosion. So here you have uh, heat exchanger, where the corrosion inside leads to decrease in the thermal conductivity of the metal. So in a heat exchanger, you want uh, to cool something and to heat the other thing. So suppose you have hot oil running through it, and you want to heat, cool the oil and heat some water. So physics heat exchanger would do that. So if you have corrosion on the surface, so water inside water, if you have some corrosive metals or oxygen present, it will corrode and form a thin layer on top. So this is all the rust. This will prevent effective thermal conduction of heat from inside to outside or to these layers. This was an example of hydrogen corrosion. Hydrogen resistive corrosion or HIC, hydrogen induced corrosion. or hydrogen-induced cracking. So what happens there is the steel, this reaction vessel has some hydrogen atoms inside, hydrogen molecules. As you know, hydrogen is a very small molecule. It can diffuse inside the metal, and as it diffuses inside, it will lodge itself inside the metal matrix, metal lattice, and when it goes inside the lattice, it will increase the volume of that region. So this region will have higher uh, increased volume due to addition of hydrogen inside. So suppose a hydrogen atom sits somewhere, two hydrogens sit here. This will repel and cause expansion in this lattice, and this will lead to some development of strain, and eventually, if there is sufficient such amount of hydrogen diffused inside the metal, you can get cracks. Here, there's some connector which got corroded. There are different types of corrosion, pitting corrosion. So you have this uh, like pits formed on the surface. This is the surface. You'll have pits, and uh, eventually, over time, these pits will grow. Galvanic corrosion, whenever you have two different metals, so iron and maybe zinc or something like that, zinc coated, some alloy or different grades of steel, maybe. So one would have higher tendency to corrode compared to other. So this is what galvanic corrosion is. You have two different metals. High temperature corrosion, as you'll see, the corrosion, the rust equation has a temperature factor inside. So at high temperature, it can lead to higher corrosion, stress corrosion cracking. So whenever there is corrosion, it will, so for example, in iron, Fe and Fe2O3, this has higher volume. So this, what will this lead to? It will cause localized stress development in the material, and that can cause, again, stress can lead to cracking. Crevasse corrosion, I think we showed, like whenever you have joint between two material, thin joint, you get crevasse corrosion. Yeah, so this is stress, again, same examples. This stress corrosion cracking. So if you have noticed, like, uh, old rusty bolts are difficult to open. So one reason is that as the iron is getting oxidized, it's becoming iron oxide and is expanding a little bit. That expansion leads to like the bolt getting jammed in its place. Also, there's friction playing a role. Yeah, this is hydrogen-induced cracking, hydrogen-induced corrosion, microbial-induced corrosion. So even some of the microbes, bacteria, or fungus, they can feed on metals like iron or something and give out metal oxide or something like that. Grain boundary corrosion. So the grain boundaries have higher tendency, like high energy sites. They are more susceptible to corrosion. So the regions of the grain boundary would erode first. Using grain boundary corrosion, fitting again, I showed the example. So why do we want to mitigate or prevent corrosion? It's kind of obvious. So corrosion can decrease because gas pipeline leak can cause a huge explosion. The crude oil pipeline which leaked, so it's impacting the environment. It's costs us a lot of money. If you build a bridge and you do not have corrosion prevention methods implemented, the lifetime of the bridge will be reduced significantly. Yeah, the cost of labor, the cost, like time devoted to it, yeah, the material cost, everything, all the costs are relevant. And depleting resources, again, the oxidized, suppose you have bridge on a river, so if there's rusting, all the rust would get in the river. So you need more, you need to mine more resources to build a new bridge or, yeah, loss of profit, yeah. So overall, globally, corrosion has a huge costs globally like 3.4% of the global GDP. So corrosion is a very big challenge, and there are lots of research going on to prevent or reduce the corrosion, so to save money, more green. So as in the lectures explained, like corrosion is not only just due to loss of mechanical strength. So if you have a bridge, you'd see as uh, the bridge gets corroded, its mechanical strength will decrease, and eventually things may break. Like here in the example, the pipeline would burst or something like that. But even other properties are affected, like thermal conductivity, as we seen in the heat exchanger here, that gets affected. Electrical resistance, so on, if you know, uh, all the pins, charger pins or whatever, they're coated with gold on top. That gold is there to prevent corrosion. If you, if eventually that gold layer gets eroded by regular plugging and plugging, and then the copper may get oxidized, so then you'll have trouble connecting. This is fairly common in like the old 3.5 mm earphones, headphones. After a time, their gold coating would get removed, and as you rotate or move the jack, the pin inside the jack, you get noise sometimes, decrease in resistance. You can have change in magnetic properties, optical and acoustic properties. Can also lead to increase in friction. I think someone's not muted. Okay, yeah, muted them. Mm, okay, so then we explained what is equilibrium. So suppose you have iron plus two electrons, giving you iron Fe. So in some solution you have iron bar Fe. You have Fe ions plus two. Some Fe would get converted into Fe plus two, and some of the Fe would get uh, deposited on top back. There's Fe. So this reaction is taking place in both directions, forward and back. And at equilibrium, the rate of forward reaction is equal to the backward reaction. So that's and the concentration of Fe in the solution would Fe plus 2 would not change, and also the mass of this iron block would remain same. And the potential at this equilibrium is called the equilibrium potential. Okay. Next we had the Nernst equation, like how derived. So the delta G for the any reaction which takes place can be written as minus N F E. E is the equilibrium potential. Delta G is the gift free energy. The energy change. N is number of electrons. So here in this case, N will be equal to 2 in case of iron. F is Faraday constant. F constant, which is 96500 Coulomb. E is their equilibrium potential. Equilibrium potential. So for suppose for this reaction, you would have delta G equals to delta G naught, which is the standard condition. If you are away from the standard condition, RT LMK. This is the thermodynamic equation. Delta G is the standard state. So the equilibrium constant K can be written as, we can write this equation as delta G plus RT, and then the reaction, the reactant activity of the product divided by activity of the reactant plus 2 activity of electron squared is your 2 electrons. Now using this Nernst equation, what you can write is what you can write as minus NFE equals to minus NFE naught for the standard conditions plus RT ln same thing, activity of the reactant. Fe and activity of the activity of the product and uh, activity of this two electron squared, activity of the product. So we can, if you send the minus N and F to the other side, you get E equals to E naught minus RT NF, and then activity of product and activity of that and activity of reactants. This is our formula. So this equilibrium potential is always measured with respect to something. So for a like slide, suppose you have a metal. Its equilibrium potential is always referred to with respect to some standard reference cell, reference electrode. So the, we define the hydrogen cell H plus plus electron. Yes, H. By definition, we define this as the standard state electron potential in zero. So everything else is the chemical potential of every other reaction is defined with respect to this reaction. So this is your hydrogen cell, so we'll have hydrogen pumping, hydrogen gas, H2. So that we'll have a platinum wire. So this is at 1 atmosphere of H2. This H plus concentration is also 1. And then whatever potential you measure with respect to this standard reference electrode, that is at equilibrium, that is the equilibrium potential for that sample. So between these two, you have a porous channel. You need diffusing of electrolytes from uh, one electrode to the other to maintain the circuit. Electrons would probably go from, if there was some reaction taking place, electron will go and some ions would diffuse this way. But at equilibrium, the no electrons would flow. Okay. But you need this voltage porous channel in between. Okay. So for any reaction, so suppose Fe plus H plus, sorry, H plus, you see H2 twice plus Fe plus 2. For this reaction, what you'll write is E equals to E naught. Here E naught would be overall E naught for this complete reaction. So this has both reduction, oxidation and reduction both are happening. So minus RT minus RT. And so activity of for any solid is assumed as 1. Solid is equals to 1. The activity of any solution becomes the concentration of that reactant in the solution. So in this case, this would be ion concentration in the solution, and similarly H plus again seen there in the solution. Its concentration will be equal to the activity. And for gas, the activity is defined as the partial pressure of the gas. Activity of the gas. Okay. Wait a second. Hello. Sorry. For gas species, activity is defined as the partial pressure of the gas. Okay. So here you would get activity as a reactant of pH, rush pressure of hydrogen into concentration of Fe plus 2 divided by concentration of H plus squared, since it's 2, and activity of iron, activity Fe, which is for solid, it's 1. It's RT. And partial pressure S2, Fe plus 2 plus the and then there. Okay. Mm, so next for galvanic cells, E cell is always a corrosion ridiculous. E cell is always positive. So another way to think, like E cell positive denotes that the reaction is spontaneous, and any corrosion reaction taking place is occurring naturally spontaneously. So the E cell will be always positive for the reaction. Okay. And E cell is defined as E cathode minus E external potential of cathode minus external potential of anode. So if you ever like remember this, whenever you have two species, you may be given as the reaction at anode. And this is the reaction occurring at anode, and this is the reaction occurring at cathode. What is the cell potential? Cell potential. Okay. This I think is already on. Okay. So just remembering some values. So E equals E naught plus RT and ln activity of um, reactant. So another way to write is the reactant side is in the oxidant. So Fe plus 2 plus, no, sorry, Fe plus H plus. We have two equations. Metal plus 2 electrons. Metal 2 plus 2 electrons. Metal. This is the oxidation reaction, and this is the redox reaction. Or it's a reduction reaction. Yeah, redox. Reduction. And what you can write is this is activity of oxidation reaction divided by activity of reduction half. So to get the values of this constant, one is you can convert ln to log, so naught plus 2.303 RT log base 10 activity of oxidation reaction reduction half divided by NF. R is 8.314 joules per mole Kelvin. F is 96500 coulombs. And N here in this case will be N, we're just leaving it as it is. So that will depend on the reaction. And temperature, if it's the room temperature, then 273 25 degrees Celsius, that's 298. So we get E naught plus 2.303 into 8.314 into 298 divided by n times 96500 and log of oxidation half. So this is multiplied by log of activity of oxidation reaction reduction reaction. So this entire thing becomes E naught plus it becomes 0.059 divided by n log. So this, if you're given the reaction is taking place at room temperature, just remember this value, but sometimes we just get approximately 0.6. Okay. So in lab, how do we measure the reaction potential? It's not always convenient to use standard hydrogen cell, hydrogen electrode. So what we do is we measure some standard electrodes with relative to the hydrogen cell, like LMI is HEAGCl, sorry, HESECl, or you can AgAgCl electrodes or AgAgCl, or you can have mm, these are the two most common used ones in the lab. The thermal and the AgAgCl electrode. So you measure their uh, standard cell reaction potential with respect to the hydrogen cell. So suppose saturated calomel electrode is plus, that is plus 0.244 volts. So whenever you do measurement with this calomel saturated calomel electrode, whatever potential you get, you add 0.344 and you'll get the reaction equilibrium potential uh, with respect to hydrogen reference standard hydrogen electrodes. You can convert them. Okay. Mm, if you had some examples, suppose you have iron in one normal H2SO4. I'll go on a tangent, so I'll explain what is normality. So you all know molarity. Suppose you have HCl dissolved in water. So 1 mole HCl in 1 liter water. So this HCl will completely dissociate into H plus and Cl minus in the water. So you'll get 1 mole of hydrogen and 1 mole of chloride ions in the solution, right? So what molarity is? It's number of moles in solution divided by volume of solution in liters. Okay. So in this case, if you have 1 mole of H plus ions, plus and 1 ml, 1 liter solution, so you get 1 mole, 1 molar concentration. Okay. Okay. This is molarity. Normality is, so this is again one normal solution. So in this case, molarity and normality would be equal. So this is also one normal, but it will be different from H2SO4. H2SO4. So if you dissolve 1 mole in 1 liter water, you get 2 moles of H plus, right? So the molarity of H plus ion molarity here is 2 2 moles per 1 liter, so it's 2 in the molarity, right? And however, this is also one normal of H2SO4. So, so 2 molar of H plus. So we added 1 mole of H2SO4. So the molarity of the H2SO4 solution is 1 molar, right? Since we are adding 1 mole. So molarity of H2SO4 is equal to 1 mole divided by 1 liter. So it's 1. However, since you're getting 2 moles of H plus, so normality here is 2 actually, 2 normal solutions. So that this gives you how many H plus or how many uh, OH minus you're getting. Okay, so in this case, if you dissolve 1 mole of H2SO4, you get 2 normal solutions of H plus ion. Not H plus, this is 2 normal solutions. So formula would be normality is equals to molarity into uh, n factor. So n is here is 2 for H2SO4. So we're getting 2H plus ion. Okay. An example he had Fe in 1 normal H2SO4. 1 normal H2SO4 just means uh, you have 1 mole of H plus ion in the solution. So that's half molar solution. Half molar solution of H2SO4 is equal to 1 normal. So if you just see the formula, again, normality equals to, you get 2. So normality is 1. So you get 2, the n here is 2. You get 2 H plus ions into molarity. So molarity here is half molarity of H2SO4, not H plus ion. Okay. And we have Cu in 1 normal H2SO4. So we want to see this, if you have a copper bar inside S1 molar, 1 normal H2SO4, we have solution here which is 1 normal H2SO4, and here you have, in one case you have copper, in the second one you have iron. Okay. And 1 normal H2SO4. So we want to see if iron will corrode or not. Iron and copper, whether corrosion will take place or not. Okay. So the standard, we're given the standard cell potential for copper. So copper plus 2, copper 2 plus 2 electrons is equals to Cu. The standard potential of this reaction is plus 0.337 volts, and for iron, Fe plus 2 plus, the 2 electron, and it Fe. Okay, so we are assuming here the partial pressure of hydrogen is 1 atm in both the cases. Partial is to 1 atm, and your other half, the reduction half, this is the oxidation half. Actually, where so plus 2 electrons. Yeah, that's 2. Here 2h plus 2 electrons. Yeah, that's 2. So the overall reaction taking place, there is Fe plus 2h plus gives you Fe plus 2 plus H2. Since this is at 1 atmosphere, so delta E cell is equals to E cathode minus E anode. This is the cathodic reaction, and this is anodic. So anodic is this number where the oxidation is taking place. Where the oxidation is taking place. Right. So your iron is actually getting oxidized. So this is the anodic part of the reaction. So 0 minus. Oh, I forgot to mention. The standard uh, cell potential is minus 0.44 volts. Minus or minus 0.44, you get 0.44 volts. And in this case, you have Cu plus 2H plus Cu plus 2 plus H2. Here again, if you see E cell, E cathode minus E anode, 0 minus of 0.337 minus 0.377. No, 337. So E cell is negative, copper will not corrode, only iron will corrode in this solution. One normal expression for next we covered the concept of pH. So what is pH? pH is just minus log of HN concentration. Okay. So if you have dissolved 0.1 mole HCl, it will dissociate into 0.1 mole H plus and 0.1 mole Cl minus. So if it is so if you dissolve this in 1 liter water, you get 1 molar solution, 0.1 molar H plus ions, right? Equal to 0.1 moles divided by 1 liter, 0.1 molar solution. The concentration is 0.1. So pH here would be log base 10.1 equals to minus log 10 into power minus 1, 1 log 10. So minus 1. It, log 10 to 10 is 1, so you get pH of 1. There was also some thing called solubility product. product. So I think this is represented as K, right? So KSP for suppose you have a reaction use NaCl. You're dissolving NaCl in water. Plus, you get Na plus and Cl minus. Solubility product KSP for this reaction would be concentration of Na plus into concentration of Cl minus. That's it. So if you had MgCl2, Mg plus 2 plus 2Cl minus, here the KSP would be Mg plus 2 into Cl minus square. So whatever the what do you call it, relative concentrations, whatever the number of moles are, that goes in the exponent. I think there's one question in the assignment which asks what is the solubility product. I think we're given solubility product or something like that. Mm, Usually we had access to the previous assignment for the previous years, but mm, previous year the assignment is same as the last year. So what I usually used to do is take solve the previous year's assignment that would help solve this year's assignment. So what I do is try to find some questions. So if you have Cu plus 2 plus Cu reaction, so we are given the standard potential for this reaction was like, this was given as 0.338, 0.337 plus 0.337. If you are given concentration of concentration Cu plus 2 is given. And 10 to the power minus 3 mole left. Okay, and this is E dot of C plus 2 Cu. Okay. So we have to find equilibrium potential. Find equilibrium potential. So we have this reaction Cu plus 2 plus 2 electrons with Cu with E cell E is equal to E naught minus RT and F log of concentration Cu activity of Cu divided by activity of copper plus 2, which is the concentration Cu plus 2, right? This here given as 0.337 minus RT will include this is 0.059. So instead of 2 electrons, 2. Yeah. Mm, yeah, this is a plus. So plus here. Okay. Activity of copper metal is 1. This is the concentration. Concentration is 10 to the power minus 3. So 10 to the power 3, 0.333 plus 0.059, 2 by 3. So 237 plus 0.059 into 3 by 3, 0.337 plus 0.0885. Will be 0.4255 volts. Okay. Mm, direction to- I'll just leave. Yeah, second question. Mm, So here we have a piece of zinc immersed in copper sulfate. At what concentration ratios will zinc stop corroding? So I'll just like give you a hint like what you have to do. So on one side of the reaction we have zinc plus two electron goes to zinc, and this you are given the standard potential. And on the other side you have Cu plus two electrons, which is Cu, and this is 0.399. And we're asked what is the concentration of Cu plus 2 and Zn plus 2. So what we'll do is just calculate the equilibrium potential for this reaction. So suppose just assume some concentration U plus 2 x. And just write the reaction in the equation. We'll have so assuming this concentration, find the equilibrium potential for the copper reaction. So I'll call it like EQ for EU, and that should be equal to the equilibrium potential for the zinc reaction. Zinc, this zinc reaction. Whenever these two would become equal, the corrosion would stop. Just satisfy this equation. And here you are assuming some Cu concentration, sorry, zinc concentration is in Y. This will be in terms of X, this will be in terms of Y. And you're asked to the ratio of X and Y. Just calculate this and yeah, you'll get the answer. Standard the equilibrium potential is E RT and ln activity of product and activity of reactant. So one side you have metal, so it will be just either 1 over, I think it will be 1 over x, something like that. And just write these two equations, taking x and y, just equate them, and get the answer. Mm, question what is the equilibrium potential for I think it is just simple. Mm, mm, mm. And you're given different concentrations, so you have a reaction Fe plus 2 electrons, Fe, delta E naught. You're given Fe plus 2 to Fe, and it's minus 0.44 volts. And we know the equation, we use E naught minus 0.059 divided by 2. Yes, here n is equal to 2. Careful of that. And log of activity of Fe is 1 divided by concentration of Fe. Just put the values of different concentration and we'll get value of E naught. E naught here already given. So just and the values of E getting a different concentration. Next you're asked to calculate pH. So I just told you. So in water, concentration of H plus into concentration of OH minus is equals to 10 to the power 14, right? Or minus 14. Like 10 to the power minus 14. So if you're given like 0.1 molar NaOH solution, so here you have uh, 0.1 molar OH uh, OH minus concentration here is 0.1, right? It will dissociate completely into Na plus and OH minus. This is the OH minus concentration. So using this, you can calculate the H plus ion concentration. So H plus ion into OH minus and into 1 minus 14, which is just 0.01. So H plus 10 to the power minus 14 divided by 10 to the power 0.1. So this is 10 to the power minus 13. So you get the H plus ion concentration and pH is equals to minus log of H ion concentration, right? So minus log of 10 to the power minus 13. This is minus of minus 13. So 13. So pH is 13. Another way is pOH. You can also calculate, which is 14 minus pH. In this case, it will be 1. pOH is 1. pH and pOH. Normality, I've already told you. Okay, if I was not clear, I'll repeat it again. So the constant in aqueous solution, the concentration of H plus and multiplication of the product of the H plus ion concentration and the OH minus ions is 10 to the power minus 14. If you are given suppose 0.1 molar NaOH solution, so you have OH ion concentration here is also 0.1 molar. Using this equation, this relation, you can get H ion concentration, which is 10 to the power minus 13. And using the pH formula, minus log of H plus ion concentration, you get pH is 13. Okay. Next, a copper storage tank contains dilute sulfuric acid at pH of 0.1, is blanketed with hydrogen at 1 atmosphere. Calculate the maximum Cu plus 2 contamination of acid in moles per liter. What is the corresponding contamination of the hydrogen partial pressure? Okay, it's different question. Now, what happens if the partial pressure of hydrogen is reduced to 10 to the power minus 4 instead of 1 atmosphere? What can be its concentration if the acid is close to 10 to the power minus 4 oxygen? So, here, so the copper dissolution, the dissolving, the copper will dissolve until the cell potential becomes equal for both sides, right? So cell potential for E cell for Cu will become E cell for H2. Whenever this condition will be satisfied, the reaction will stop. And yeah, so that will be the maximum copper plus 2 ions in the solution. Okay. So this is just the molarity. You're asked the molarity here. Just write the copper, the electrode potential for the equilibrium potential for copper, and on left hand side, write the equilibrium potential for hydrogen. In case of copper, you will have something like E naught for Cu plus 2 to Cu plus 0.059 something copper log of copper concentration U plus the concentration, and on this side you will have E naught hydrogen, which is 0, right, plus 0.059 divided by this again has 2 log of H plus ion divided by partial pressure of H2, and just equate these two sides and you'll get the value of H copper U plus 2 ions. Okay. So given the pH, so you can calculate the HM concentration. You're given the hydrogen partial pressure, so just calculate the copper ion concentration. And next part, you're just changing the partial pressure. So instead of 1, put 10 to the power minus 4, and you get a different ion, copper ion concentration. Okay. And in third part, you're given third part, instead of hydrogen getting reduced, you're given what if oxygen is getting reduced. So 4H plus 4 electrons gives you twice H2O. This is the reaction taking place where you're given activity of water is 1, partial pressure of oxygen you are given, right? This concentration of H plus ions is given, right? You are given pH. So this will be like 1.23. The equilibrium potential for this would be 1.23 minus plus 0.059 divided by 4, because there are 4 electrons getting transferred, log of H plus ion to the power 4, and again equate these two equations and we'll get the copper ion concentration again. Okay. Okay. Lucky next in the next session I'll go over individual. I'll go over the exact solution for this first assignment. Okay. I have some question. Decreasing the concentration of metal ion will increase anodic behavior. So suppose we have a metal close to metal plus 2 electrons. So if you're decreasing the metal ion concentration, the reaction would be more anodic. So anodic reaction is the oxidation part of the. This is the anodic reaction. So if you're reducing the metal ion concentration, the reaction will proceed more in the forward direction. So it's an equilibrium, so metal plus two electron. So if you're reducing the metal ion concentration, the reaction will proceed more toward this end.
Can you please come to the slide number 23?
23. Yeah.
Here on decreasing the metal ion concentration, we have decreased the metal ion concentration to 10 raised to the power minus 3 moles. And here the behavior is shifting towards cathodic.
Okay. I think I've made wait. So I think I've done this mistake. There should be a minus here, right? So this is the product. So copper, its activity is 1, and copper plus 2 concentration is at the bottom. So this becomes plus 3, minus, minus, minus. So it will be reduced. Yeah.
Okay, thank you. Got it now. Can you please come to the last slide?
Last slide. This one?
Yeah, the last question that.
Oh yeah, this one. Yeah.
Yeah. Here, in the first case, the two reactions are, one is the copper metallic reaction, then it is we are balancing it with the hydrogen reaction.
Yeah.
And in the second case, we have that oxygen and H2O, that reaction is a reduction reaction, and again metallic reaction is the copper reaction.
Yeah.
So in the second case, whether both reduction reaction will not take place simultaneously, because we have oxygen also, then the oxygen reaction will also take place, and again we have H plus ion in the electrolyte. So
I get your point. Yeah. Mm, I think we can.
the anodic reaction will be balanced by two cathodic reaction.
Yeah,
What
I
I
get your
think in this
point.
case.
So we can you can do the calculation and see if the oxygen part is more significant, the hydrogen part, hydrogen reduction might be comparatively less. So we'll have to check if you do the complete, include both effects. Actually, we should include both effects. I think, yeah. Maybe the concentration is close to, but I don't know if it's combining both the things it's the blanketed with hydrogen and it's getting exposed. So if both things are happening simultaneously, according to the solution I have, they've only considered the just the oxygen part.
So for simplicity, we have to consider only oxygen part.
Yeah.
Otherwise,
Otherwise it'll be difficult. Yeah, and I think just use the oxygen part to solve the question. Yeah. Okay. Any other doubts?
I have one more question. Which book we can refer to get these sort of problems, where we can get these sort of problems, so that we can practice it?
Book. Uh, did the professor mention any books in the course? I don't know if they have practice questions as well. I can check and let you know in the next class.
Okay, fine, thanks.
Okay. Looks for practice question, right? Okay. I'll check the books the sir has recommended to see if the practice questions. Okay. Any other questions? Okay, then I'll end the session here. Next week I'll go through the exact solutions. And if you guys have different questions, different solutions, and one asked, like if the solutions are incorrect or whatever, you can also sum up. Ask. Okay. Okay then. Thank you for attending. Bye.